All right, this is the video for section 8.2 notes, slides 23 and 24. All right, so basically, when we get down to it, we need to make sure we understand how to find a volume by rotation, right? No matter what we're given, right? So, in summary, to find a volume of rotation, we're going to draw a region. Okay, we draw whatever region we're given, and then draw a dx or dy rectangle so that the boundaries do not change. Okay, so that means we want to do whatever we're doing with one integral, right? Okay, so for instance, let's say that I have this graph here. I have a parabola facing downwards, and then I have some sort of a line here. Now, if I want this region right here, okay, it makes the most sense for me to use a dx because if I move the dx right and left, the upper boundary is always this curve and the lower boundary is always that line. However, if I were to choose a dy, that would mean I would need two separate integrals because of this point right here where the right hand boundary would be the curve up here and then the line down here, right? So that's what I mean when I say choose so that the boundaries do not change. Okay, now what if I selected this other region here? Now, if I selected this region, what would it make the most sense to use? Well, it would make the most sense to use a dy rectangle now, because no matter where I move within the region, the right-hand boundary would always be the curve and the left-hand boundary would always be the line. However, if I chose to use a dx, I would need two separate integrals because the upper boundary would be the line over here and the curve over here, right? So that's kind of the idea behind draw a dx or dy so that the boundaries do not change. All right, now in that discussion, I didn't ever think about disk method, washer method, or shell method, or whatever, right? Why? Well, because if I'm going, let's say I have this region once again, okay? And we already said that it would make the most sense to use a dy rectangle, right? So now I say, okay, I'm going to use a dy. Then I want to check what the axis of rotation is, right? So let's say I'm going around a vertical line, then that means this is perpendicular, and so I would use the washer method, right? But what if we were going around a horizontal line, right? Now dy is parallel to the horizontal line, and so then that means we're going to use the shell method, right? So if parallel, use shells. If perpendicular, use discs or washers, right? So that's kind of the idea. That's how we tackle these problems when you're not told what to use, okay? So now let's go on to slide 24. Write an integral that represents the volume. So we're not actually going to carry it out. We're just going to write an integral that represents the volume generated when the region bounded by x equals y cubed, x equals 8, y equals 0. All right, so x equals y cubed, that is this curve here, right? Now remember, x equals y cubed is the same as y equals the cube root of x, right? Those are the same graph, all right? But depending on whether we're using a dx or a dy, we may want x equals y cubed, or we may want y equals cube root of x. All right, then I have x equals 8, which is a vertical line right here, and I have y equals 0, which is this horizontal line, right? Okay, so now we're given x equals y cubed, and so I'm just going to say, well, let's just stick with a dy. Now, I could choose a dx. Neither of these would have boundaries that change, right? And so either one is fine, all right? Now, I have going around y equals 4. So let's start with that. Y equals 4 would be above my region here, right? And so that's going to be a parallel to the dy, right? So parallel is going to mean use shells. So I'm going to write shells, okay? Y equals -2, that's down here once again. So that is parallel. And so we're going to use shells. Okay, now remember the setup for shells is what? It's 2 pi times the integral of radius times height, and then with respect to y in this case. All right, so then I set up shells here, 2 pi times integral of radius times height with respect to y. All right, now for C and D, right, let's look at x equals 10, x equals -3. So now I'm going to change the color here so we can see it. All right, x equals 10 is a vertical line over here, right? The vertical line is perpendicular to the dy. So I'm going to use the washer method. Now remember, the washer method and not the disk method because there is a gap between the region and the axis of rotation. All right, x equals -3, that would be a line, vertical line over here. Once again, dy is perpendicular to that vertical line, so we're going to use the washer method. All right, now remember the setup for the washer method is pi times the integral, and then I do big parentheses with respect to y, and then I have big R squared minus little r squared. Same setup for d, pi times integral of big parentheses dy, and then I have big R squared minus little r squared. Now, I highly recommend that this is how you set up any of your problems before you put in any of the specifics. You get it set up for shells or washers, okay? So now let's go back to A. All right, so for A, it says y equals 4, right? So y equals 4 is above the region, right? So now we take the radius. Now remember, the radius is the distance that the rectangle is from the axis of rotation. So the rectangle is a height of y, right? And the axis of rotation is a height of 4. So we're going to take 4 minus y. Remember, we're taking like the upper thing minus the lower thing, okay? Times the height. Now remember, the height represents the height of the dy. So that would be the upper boundary of the dy, which is 8, minus the lower boundary of the dy, which is y cubed. Now remember, we're using y cubed and not the cube root of x because we're doing a dy, so it needs to be an x equals form. Okay, and then we're integrating from, remember, it's with respect to y, so it's a y value. So lowest y value is 0, and the highest y value, well, right here, that is when x is 8, so that means y is 2, right? Because if y is 2, 2 cubed is 8, right? So we're integrating from 0 to 2. All right, what about for B? Y equals -2. Well, now y equals -2 is below the dy, so we're going to take y, which is the upper thing, minus -2, and then the height is still the same, 8 minus y cubed. All right, and we're integrating from the lowest to the highest, so 0 to 2. All right, so that's part B. All right, part C, x equals 10. All right, so now we are integrating, okay, with respect to y still, but now it's a washer method. So now x equals 10 is to the right here. So which boundary of the dy, the right-hand boundary or the left-hand boundary, is further from x equals 10? Well, the left-hand boundary, right? So big R is going to be 10 minus the left-hand boundary. What is left-hand boundary? Well, it's that curve, right? And so the curve is y cubed, right? And then, so 10 minus y cubed squared minus, all right, the small r. So that's going to be the distance that the axis of rotation is from the nearer boundary, which is the right-hand boundary, or 8. So we're going to take 10 minus 8 quantity squared. All right. And now, once again, we're still integrating with respect to y. So we're integrating from 0 to 2. All right. Now the washer method for x equals -3. Now x equals -3 is on the left of the region. So now which boundary, the left hand or the right hand, is further from x equals -3? Well, now the right hand is. So we're going to take 8 minus -3. Remember, we always take the right hand thing minus the left hand thing. So 8 is on the right of -3, right? So we take 8 minus -3. On the last problem, we did 10 minus 8 because 10 was on the right. Okay. Now, okay, little r, we take the nearer boundary to the axis of rotation. And so we're going to take y cubed minus the axis of rotation, which is -3. Remember, the left-hand boundary is on the right of the axis of rotation. And so then we're going to integrate from 0 to 2. And that is slide 24. Now, we very easily could have done the same thing, except used a dx, and then we would have basically switched. A and B would have been using washer, and C and D would have been using shell. And that would have been just fine as well. Okay? All right, so that is slide number 24.